Cool. Well, welcome back, everybody, to another exciting session of CE 397, Controlled Theory for Smart Infrastructure. So what I want to do first, before I get started with the class material today, is just talk a little bit about the course project. So you can find this on Canvas under Files / Course Project Documents / I think this is just titled Project Guidelines.pdf. So you can go ahead and find this and follow along if you wish. The first thing you might want to note is the due date, which is officially listed as April 20th, 2023. But note this asterisk here. So officially, the project report is due on April 20th, which is the last day of class at 11:59 p.m. However, final project reports will be accepted without penalty anytime until Sunday, April 30th at 11:59 p.m. CST. So you get an extra 10 days from the official due date to turn it in. And that is during the final exam period. So the official due date is on the last day of class, but you can turn in anytime before 11:59 p.m. at Sunday, April 30th, without any penalty. Okay. Are there any questions on that due date? Questions or concerns? Okay, so that's about a month from today. And note that I will be a bit more strict on the late policy with the course project than I am with the homeworks. So any project report submitted after 11:59 p.m. Central Time on April 30th will get an immediate 25% penalty. I have had to exercise that in the past, so please make sure you turn in your report on time. And you can turn in the report anytime up until that deadline, so you don't have to turn it in on April 30th. Anytime before 11:59 p.m. On April 30th is when the report will be accepted without penalty. Okay, and then reports submitted more than 24 hours late will not be accepted. Okay, so this is this project report is about 30 to 35% of your final grade. So I would recommend making sure you submit it on time. Okay. And I will put up a assignment on Gradescope for you to submit the project report. After the project report is done, I'll post a separate Gradescope assignment in which I review your paper and kind of post a long review of just my evaluation of the project report and potential room for improvement. Okay, are there any questions on the deadline or late policy? Okay, so note that this is for the project report. There are two components to the final project, two primary deliverables. The first is the project presentation, which will take place on the last day of class. I'll get into a little bit about what I expect for the project presentation, but that is worth 10% of the project grade, and the project final report will be worth 90% of the project grade. And again, that is due officially on April 20th, but you can turn it in up until April 30th without penalty. Okay, whereas the project presentation is in class on the 20th. All right, so as I mentioned before, really you can do anything for these projects as long as it fulfills my two criteria. One being it has to relate to civil engineering in some substantive way, and second, it has to relate to the material taught in class in some substantive way. And for most of you, I've already approved a project. If I haven't explicitly approved a project for you, please see me this week so that we can talk about it and get one approved. And also, I will, be encouraging you to come see me in office hours about your project as we wind into the final month of the class, just because I want to make sure you're all on the right track here. Okay, so let's go through the project presentations. As I mentioned, there's really just two criteria here. scope of the project can be pretty flexible. I think I've approved, projects for most of you. Let's talk a little bit about the project presentation. So on the final day of class, each project, so note that officially the class project can also be a team project. I don't know if I mentioned this explicitly, but you are allowed to work in teams for your course project. So on the final day of class, each individual or project team will present a summary of their findings as an oral presentation. And the guidelines for the project presentations are pretty strict. I did it this way on purpose just to make sure that everyone has adequate time to present. And then also to make sure that your project presentations really kind of get the most, just represent your project very concisely, so that it kind of forces you to think about what material you want to present and what's most important, which I think is important for your professional development as well. So I do have pretty strict guidelines for the project presentations. Your presentation has to be 4 slides and must be 4 minutes long total. Now, note, I might adjust the timing slightly, just depending on, because this class is a bit larger than my class from last semester. So I'll post a note if I think this is not going to be feasible. But for now, expect 4 slides and 4 minutes for your entire presentation, so about 1 minute per slide. So the first slide is kind of your general introduction slide. It should describe your research question. And really the point of this slide is to motivate your presentation. So why is this research topic important? Are you doing something that hasn't been done before? Are you filling a knowledge gap in the literature? And does your project have any potential real world applications? So this slide is to introduce the problem that you're looking at and convey why it's important. Okay, second slide will describe the methods that you use to answer your research questions. So note that this is out of all of your 4 slides, you only have 1 slide to present your methods. So make good use of this slide. Essentially, just any methods you used to, any methods you developed or any methods that you used to solve the problem that you looked at. Indicate if you did anything novel methodologically. So if you developed, for instance, a new control algorithm or paired 2 things together that previously had never been paired before or something like that, just make sure to indicate any novelty in your second slide describing your methodology. The third slide is the most important one. This is the one slide that presents your results. So to assist you, I would recommend just choosing a single figure that really represents your core findings and then explain the significance of the figure. So for instance, you may have a project where you're looking at state estimation in a water distribution network, let's say. So you're trying to estimate the internal states inside a water distribution network. This slide might be a slide or a picture or an animation just showing the reduction in error of your estimate of the internal states in your water distribution network under your filtering methodology or state estimation methodology or something like that. Or if you're looking at a control problem, it might be an image just displaying what the control performance is, how well are you able to achieve your objective using your new control algorithm or something like that. Okay, so just basically, I would recommend just doing one figure, explaining your results and their significance. And then the fourth slide discusses the broader implications of your research. So again, I think this is kind of describing your core contributions, just reminding the audience what your core contributions are, why your results matter. This can either be results in terms of, what we might call broader impacts, like does this study have any kind of practical uses, any potential practical uses that might help solve societal problems, or did you create a really compelling intellectual contribution? So for example, developing a new control algorithm looking at a concept in a way that had never been looked in before or something like that. And particularly, I want you to describe how your study fits into the existing literature. So what new thing did you do with this project? Okay. Are there any questions on the project presentation? Oh, and note quickly, you don't need to include a title slide, although, you know, I won't penalize you if you have a title slide. So these are the 4 key slides I want you to present on. Okay. Are there any questions on project presentations? Any questions? Okay. As for the grading of the project presentations, basically, I'm going to look to see if you met the guidelines specified for each of those slides. So in your 4 slides, did you hit all of the points that I was looking for? So did you convey the novelty of your work? Did you present your methods in a way that could be understood, but that also, wasn't too bogged down in the details? So that's the main criteria I'm going to assess your presentation on. Did you meet the guidelines? Did you convey the significance of your work? And then also, was your presentation engaging and were you prepared? So I would encourage you to practice your presentations, or at least write down what you're going to say beforehand before you go to present. All right. Any questions on the evaluation of the presentations? All right, let's talk a little bit about the project report requirements. So I posted some examples of project reports that you can look at. So based on those examples, your project report should be about 5 to 10 pages, including citations. The length isn't really the most important part to me, although you do kind of need a report of that length to describe your methods and describe your results, present your figures, and so on. So I would say 5 to 10 pages would be appropriate. Citations in IEEE format, and you can include supplemental material as needed in an appendix to the main report. And you should submit your report as a PDF file to Gradescope. So the final report should have the following structure, and I would like this structure to be followed exactly. So you'll have an abstract, introduction, literature review, methods, results, discussion, and then if you worked as a team, just a short description of the division of work among the team. If you wrote any code for the project, it should be included in the supplemental material. So you can either upload code directly or print out a PDF of the code and include that in your PDF document. Okay. Also, if you used any external data, a link to the data or a copy of the data should be provided. And note, in Gradescope, I don't know if they allow you to upload zip files or code or anything like that. So just send it to me via email if you used any code or external data. All right, let's talk a bit about the grading. There's 4 main components to how I'm going to be grading the reports. And I will note that you should expect the grading to be a bit more stringent than how I've been grading your homeworks. So in general, I would like to convey that I would like this project to be something that may potentially be publishable someday. So I do have pretty high standards for these projects. Many of them did eventually turn into research projects that students in previous versions of these classes used for their research. So I would encourage you to use this course project as effectively as possible. Use it for something that you're going to use for your research. With that said, I will be grading it pretty stringently. I would expect the average grade for the course project reports to be something like in the high 80s to low 90s. So kind of in the, on average, like a B+. There are people in previous classes who have really gone above and beyond and who have delivered projects that are, potentially close to being publishable. I would say that like getting 100% on this project would be like turning in a paper that is ready for publication in a good journal. Like a 95 might be turning in a report that is, potentially publishable with some extra work. And then kind of the average performance I would expect is about like a 90 or high 80s, which may be potentially publishable with some major revisions. But that's about what I'm expecting for the project. Okay, are there any questions on that grading policy? And note that the overall grades for the class are curved, right? So the average grade for the class will be at about an A-. Just because the average grade on this project might be like a B+ range, that doesn't necessarily mean that you'll get B+ and so on. The whole overall grade is curved. All right, let's talk a bit about the components of the project report grading. So first, clocking in at about 25% of the overall grade is the quality of writing. So I really want to emphasize that quality of writing is important if you're going to become a researcher, a scientist, or if you're going to work in any kind of capacity as a leader in industry. You really need to know how to write well. So I'm going to be grading pretty critically when it comes to the writing. So in particular, what I'm looking for is, is the paper well written? Now, I know that not everyone here, learned English as a first language. That's not really what I'm looking at here. What I'm looking at here is how well is the paper structured? Do the ideas flow together cohesively? Are the paragraphs full of, are they empty of filler? So does every sentence and paragraph have a point? Things like that. So it's more about how the paper is structured, whether you're conveying your ideas clearly, and so on. And in particular, I want to make sure in these reports that you're conveying the contribution of your study. So make sure to highlight what is the novelty of the work, how does it fit into the existing literature, and so on. Also, are the methods clearly explained? Are they explained clearly enough for the results to be replicated? And are the figures effective at conveying the information that you want? Okay. So again, this isn't, this is more about conveying ideas clearly, making sure the paper is structured in a way that's easy to follow, make sure that it's written in a way that I can potentially replicate the findings, and not so much about, being like a wordsmith, for instance. It's more about just conveying your report clearly. Okay. The second component is novelty. So this is more about how just the conception of the study in general. So is your idea original? Does it fill a knowledge gap in the literature? Does it have any important real-world implications, broader impacts? And as with the first section, is the novelty properly communicated? Do you incorporate concepts from the course in a creative way? So this is just general originality, novelty and originality of the work. Third is technical merit, and really this encompasses how well you're integrating the material from the class. Does it show a mastery of material from the course? Does it show a understanding of the research topic that you chose? Are the methods sound? Are the methods technically and theoretically sound? Are you modeling any real-world physical processes in a sensible way? And are the mathematics at a level that's appropriate for the course? So this is kind of the technical component of the report. How strong is the technical side? And finally, study design. This is probably the hardest to describe, but really this is about whether or not you are presenting a way to evaluate your work in the context of other work in the field. So for instance, do you present a testable research question? Do you present a hypothesis? If not, do you present a way for evaluating your contribution? So for instance, if you're proposing a new control algorithm, do you assess its performance relative to other existing control algorithms. Is your method for evaluating your chosen topic robust? So basically, this is how you are either evaluating your hypothesis or conveying the relative contribution of the study with respect to the existing literature. Okay, and note finally, I want to just let you know that this isn't a checklist, so you don't have to meet every single item on this list of grading criteria. This is kind of just intended as a aspirational, right? So a good study would have at least something from each of these criteria to that attest to it. Okay, cool. Are there any questions on the grading of the course project? Okay, so I would say as you're writing the course project, just review these 4 different areas and think about them as you are conceptualizing your study and writing the report. All right, great. Are there any just overall questions on the course project before I move on? No more questions? Okay, so like I said, we have about a month left on the course project. I really want you to start homing in on your topics if you haven't already chosen one. If you haven't already chosen a topic, I would like you to see me this week because it's going to be important to get that established before you start working. And otherwise, if you have any questions on the course project or just want my feedback, come and see me in office hours. I'm always happy to talk with you about your course projects. Okay, cool. Well, let's go ahead and move on. So in today's lecture, it's going to be kind of a grab bag of different topics just because I need to cover some final topics related to the eigendecomposition, and I also had to talk about the course project. So today we're just going to be doing kind of a more relaxed day in which we're just going to be reviewing some concepts from eigendecomposition, talking a little bit about generalizations of the eigendecomposition, and doing a few in-class exercises if time permits. Okay, so let's quickly review what we talked about last time. So last time we talked about eigenvalues and eigenvectors. Can anybody just tell me intuitively what an eigenvalue eigenvector pair are? Just to recap. So from this equation, we can kind of see what an eigenvalue eigenvector pair, how they behave, right? And I think Jimmy gave us a definition last time. Does anyone else want to just quickly describe what an eigenvalue eigenvector pair are for a linear transformation A? So first of all, what is the eigenvector? What's special about an eigenvector under a linear transformation?
So the linear transformation applied to the eigenvectors will not change the scale.
Right, exactly. So an eigenvector is a special vector defined for linear transformation A, for which when you apply A to that eigenvector, it doesn't change direction, but rather just scales its magnitude. So that is the definition of an eigenvector. Very good. So how did we go about computing eigenvalues and eigenvectors? So first, for eigenvalues, how did we compute these? There was a special formula that I gave you. Do you remember what it was? What was the name of that equation? Yeah, it was the characteristic equation. So we found that we could compute eigenvalues by taking the determinant of lambda I minus A and setting it equal to 0. Okay, and from this, finding the roots of this characteristic equation, we could determine the eigenvalues of our linear transformation. Okay, how did we find the eigenvectors? So to find the eigenvectors, we set up a system of equations, right? So we know from our definition of the eigenvalue eigenvector pair that we can take lambda I minus A times V, and that this V here should be in the null space of lambda I minus A. So therefore, we can find the null space, a basis for the null space of this matrix here. And in doing so, we can compute the eigenvectors of A one by one. All right. Next, we talked about diagonalization. So this is a really important topic that we're going to get into a bit more today. We're going to get into some generalizations of diagonalization. We showed that for a matrix A that is diagonalizable, and we'll talk a little bit more about matrices that are not diagonalizable today, we can decompose it into this matrix product where lambda here is a diagonal matrix of eigenvalues, lambda 1, lambda 2, through lambda n. And V is a stacked matrix of eigenvectors, right eigenvectors, V1 through Vn. And our U Hermitian is equal to V inverse, and it is equal to a stacked row matrix of our left eigenvectors. So U1 Hermitian all the way through UN Hermitian. And we also showed how this matrix product here can also be thought of as a sum of outer products of the eigenvectors of A. So it's a sum of scaled products of the outer product, a sum of scaled outer products where these are essentially the different directions associated with the linear transformation. And the lambdas are the energies or magnitudes associated with each one of those directions. We're going to get into this a bit more today. I really want to convey this way of thinking about the eigendecomposition. We're going to talk a little bit more about it when we get to the singular value decomposition. And I'll try to give you some intuition through an in-class exercise. Okay, and the final topic we talked about was the eigendecomposition in dynamical systems. So if we have a state space system of the form x dot is equal to ax plus bu, we can use the eigendecomposition to learn some important things about the state space system. And last time at the very end of class, I went through this example where we looked at our old friend, the structural system, the spring mass damper system. And we showed that when we computed the eigenvalues of this system and looked at the characteristic equation, what did we learn about the eigenvalues of the state space system? Right, so the eigenvalues of the state space system are the same as the poles. All right. So what does that tell us about the eigenvalues? In other words, what do the eigenvalues now tell us about our state space system? Right. So that's the first thing it tells us. It tells us that we can determine whether a system is stable or not by looking at the eigenvalues of the system. There's a lot of different things it's going to help us think about. But in particular, it's also going to help us solve state space systems. So remember from the first part of class, we showed that the response of a system could be characterized in terms of its poles. For a state space system, it works the same way in terms of its eigenvalues. So at the end of class yesterday, we looked at this structural system. We plugged in some actual numbers for the mass, the stiffness, and the damping. And we found that the poles and eigenvalues of the system are placed at -1, -2. So just quickly, is this system stable or unstable? right? This system is stable. Okay, so one thing I want to do now is I want to show how we can use the eigendecomposition to gain a little insight into the behavior of a dynamical system. Later on, we're going to be using it to actually solve LTI systems, using the eigendecomposition to solve LTI systems. But there's a neat trick we can use. In particular, we're going to look at how we can put the system into modal coordinates. We're going to see what information this gives us about the system. Okay, so as before, we have a system of the form x dot, x double dot is equal to 0, 1, -2, -3 times x dot. In this case, let's make it the full system, so not just the homogeneous system, but let's also include the forcing term. So we have 0, 1 times f of t. And let's also include an observation equation. So let's say we're just interested in the displacement x. And so we can write the observation equation as 1, 0 times x dot. And this will just return x as our observed variable. Okay, so in this case, we have here, this is x dot, that is our state derivative of our state vector. This is x, this here is b, this here is a, this here is c, this here is u, this here again is x bar. Okay, so we can express this as a generic state space system. We have that x dot is equal to ax plus bu, and we have that y, let's just call it y as just a generic observed variable. Y is equal to cx plus du. Okay, in this case, we'll just have that d is 0. So this is d, this is u. All right, so one thing to note is that state space representations of a dynamical system are not unique, right? For a given dynamical system, you can define infinitely many different state space representations of that system. All you have to do is change the coordinates that you're looking at. So in particular, what I want to do here is instead of looking at this, this state vector x, let's define a new state vector. Let's say that x, our previous state vector, is equal to some vector x tilde times some matrix V. So we're just defining a coordinate transformation here. We're saying that our original state vector x is equal to some matrix V times some different vector x tilde, right? We can do this. So let's see what happens if we go ahead and substitute this in to our original state space equation. Let's take x and let's replace it with vx tilde. So we have vx tilde dot is equal to a vx tilde plus bu. Right, all I've done here is I've replaced x, our original state vector, with vx tilde. We've just defined vx tilde to be equal to x. And for the observation equation, we have that y is equal to c v x tilde plus du. All right, so we can just go ahead and we can pre-multiply by v inverse. If we pre-multiply by v inverse, this goes away and comes in on this side, and we get v inverse a v x tilde plus v inverse bu. Okay, so what about this term here? Does this look familiar to anything we looked at before? So what is this? What does it look familiar to? Yeah, it looks familiar to our definition of diagonalization, right? So we said that we could find if A is diagonalizable. If A is diagonalizable, we have that A is equal to V lambda V inverse, right? So if we just pre-multiply by V inverse and post-multiply by V, then this becomes lambda is equal to V inverse AV. So we can take this expression here, and what is this equal to now? If we define V to be the right eigenvectors of A, what is this expression equal to? Right, so it'll just be equal to lambda. So if we're able to find a V such that V is the matrix of the right eigenvectors of A, we can apply a coordinate transformation to diagonalize our state space equation. So this is called putting the state space equation in modal coordinates. So let's go ahead and do this with some actual numbers. So note that we have an A matrix of the form 0, 1, -2, -3. A is equal to 0, 1, -2, -3. What is our lambda matrix here? Right, so it'll be -1, 0, 0, -2. What about V? So we actually computed the V matrix already. I just didn't tell you what it was. If you go back to our previous class, we computed the eigenvectors of this matrix, right? So we can go ahead and write those down now. The eigenvectors happen to be 1 over √2, -1 over √2 in the bottom left, -1 over √5, and 2 over √5. And we also computed V inverse. V inverse was equal to 2 √2, √5, √2, √5. So we can rewrite our state space equation in modal coordinates. We have that x1 tilde dot, sorry, yeah, I should write it x1 tilde dot, x2 tilde dot is equal to, we'll have lambda as our new A matrix. So that'll be -1, 0, 0, -2 times x1 tilde, x2 tilde plus, so if we take V inverse and we multiply it by our original V vector, which was 0, 1, we will end up with √2, √5 times f of t. Okay, and then we have that our output y is equal to CV times x tilde plus du. So d was 0, that'll go away. We have to compute CV. And our CV, C is the row vector 1, 0. So we multiply that by V, what we will get is 1 over √2, -1 over √5. So the first row times x1 tilde, x2 tilde. And what was this y equal to here? If you go back to our original state space equation, what was our output? Yeah, it'll just be x. It's just the displacement x. Okay, so this is our state space system in modal coordinates. So what's special about having the system in this form? So what are some nice things about having the system in this form, first of all? Let's brainstorm here. What are some, sorry?
Lambda is a diagonal matrix, and it's very nice.
It is nice to look at, yes. It's very neat. So what are just some nice things about this equation? I just want you to take a little time to think about it. What are some potential nice things about putting a system in this form? Well, let me help you out a little bit. So one nice thing is that we can see immediately whether the system is stable or not. So we know its eigenvalues just by looking at it. And we can see that this system is indeed stable because both poles, both eigenvalues are in the open left-hand plane. Another nice thing about the system of equations is it is our matrix here is diagonal. And that means that the two equations are uncoupled. So we have an uncoupled system of equations now, meaning that we can, in theory, go and solve each one of these equations individually, right? So we have that x1 tilde dot is equal to negative x1 tilde plus, what is it, root 2 f of t. And we have x2 tilde dot is equal to negative 2 x2 tilde plus root 5 f of t. So both of these are just ordinary differential equations that we know how to solve. They're linear ordinary differential equations that we know how to solve. We can go ahead and solve these and then use our C matrix to transform it back into the original coordinate system, right? And so in this way, we can easily compute the response of this system. So we can find the solution by solving those uncoupled differential equations. Another nice thing about putting the system in this form is you can characterize what the dominant modes of the system are. So you know, for instance, if one eigenvalue is much larger than the other, you know that the system is dominated by a perhaps smaller set of modes. So for in this case, the structural, these will be the vibrational modes. But a final point that you might want to think about is when we get into feedback control later on, both for control purposes as well as for observation purposes, we'll want to place the poles of the system at certain locations. Having a system in modal form like this can facilitate placing the poles of the system wherever we want. Okay, so when we're doing feedback control, we generally want to specify what the poles are. Putting the system in modal coordinates makes that process easier. All right, great. Are there any questions on modal coordinates before I move on? Okay, in Thursday's class, we'll be showing how we can solve state space systems in general. And we're going to be using a similar idea to solve just generic state space systems to find the analytical solution. All right. Cool. With that, I want to cover just a couple identities. I want to revisit some concepts we talked about earlier in the class, but now I want to talk about them in the context of eigenvalues and eigenvectors. Eigenvalues and eigenvectors make some things a lot easier to think about. They, in particular, facilitate a lot of proofs. So let's go back and look at a couple of concepts that we looked at earlier in the course. So first, let's take a look at the trace. Okay. We know that the trace of a matrix A is equal to, how did we originally define the trace? It's the sum of the diagonal elements, right? So let's say we have the trace of a matrix A, it's a square matrix. And we know that if A is diagonalizable, we can write A as V lambda, V inverse, right? Now, there's another important property of the trace that I gave you. The trace is invariant under what? Cyclic permutations. So let's go ahead and cycle this by one. And we get that the trace of V inverse V lambda is equal to our original expression, the trace of A. What happens to these two terms here? Becomes the identity matrix. And we get that the trace of A is equal to the trace of lambda, where lambda is our diagonal matrix of eigenvalues. So what does this imply about the trace? Right. The trace is the sum of the eigenvalues, which is really interesting. It's not something you would expect just looking at the matrix, that the sum of the eigenvalues is the same as the sum of the diagonal elements, but it turns out to be true. Okay, similarly, let's take a look at the determinant. Okay, let's look at the determinant of a matrix A. Okay, we know that A, if it's diagonalizable, can be written as V lambda V inverse. And I don't know if I gave you this property explicitly in class, but for the determinant, we can write it out as the determinant of each of these elements in this product multiplied by each other. So we have that this is equal to the determinant of V times the determinant of lambda times the determinant of V inverse. Okay. Each of these terms is going to be a scalar, right? So we can just shift them around and write it as determinant of V times determinant of V inverse times determinant of lambda. And another property of the determinant that I didn't cover in class, but is in the notes, is that if you have the determinant of V, let's just say that the determinant of V is equal to some number alpha, and the determinant of V inverse will be 1 over alpha. And therefore, the determinant of A is equal to the determinant of lambda, our matrix of diagonal eigenvalues. So the determinant of a diagonal matrix will simply be equal to the product of the elements along the diagonal. And so the determinant of A is equal to the product of the eigenvalues from 1 to n. Okay, so this is the way I typically think about the determinant and the trace. The trace is the sum of the eigenvalues. The determinant is the product of the eigenvalues. All right, let's take a look at just two more concepts that we talked about previously. I want to talk about the nullity and the rank. Okay, so let's take a look at the nullity of a matrix A. So we know from our definition of the eigenvalue eigenvector pair that AV is equal to lambda V, which implies that A minus lambda I times V is equal to 0. All right, what if we let the eigenvalue be 0? What if we let this lambda be 0? What will this become? It'll be AV is equal to 0. Okay. And what does this remind us of? V is in the what of A? Null space. So what does this imply about the nullity of A in terms of the eigenvalues? Remember, what did we do here? We set lambda equal to 0. So what does this imply about the nullity of a matrix A in relation to the eigenvalues? That is true. So what is the nullity equal to in terms of the eigenvalues? How can we characterize the nullity of a matrix in terms of the eigenvalues?
The number of zero, like,
Right. It's equal to the number of eigenvalues that are equal to 0. And what does this imply about the rank? So if the nullity is equal to the number of eigenvalues that are equal to 0, what is the rank equal to in terms of the eigenvalues? Exactly. So by the rank nullity theorem, the rank is equal to the number of non-zero eigenvalues. Okay, so this is an important identity. Typically, when I think of the rank of a matrix, I almost always think about it in terms of the eigenvalues, because any matrix, any diagonalizable matrix, can be written as that sum of outer products of different directions scaled by those scaling factors determined by the eigenvalues. So when I think of the rank of a matrix, I'm usually thinking about it in this way. So this is a kind of important concept to wrap your mind around. The rank of a matrix is equal to the number of eigenvalues that are non-zero. All right. Right. So quickly, before I start to get into non-diagonalizable matrices, I want to give you a really important theorem. So remember I said that not all matrices are diagonalizable, and in general, it's really hard to know when they're going to be diagonalizable, but there's one particular class of matrix that we can say for sure is diagonalizable. Does anyone know what that class of matrix is? What types of matrices, does anyone know what types of matrices are always diagonalizable? So this is a really super important theorem. It turns out that if we have a matrix A, we'll say it's in C n by n. And if A is Hermitian, so if A is equal to A Hermitian transpose, then A is always diagonalizable. It's always diagonalizable with diagonalization given by A is equal to V lambda V Hermitian transpose, which we can also write as that sum of outer products from I equals 1 to n of lambda I, VI, VI Hermitian transpose. So if A is complex valued and it is Hermitian, or if it is real valued and is symmetric, that matrix is always diagonalizable. And not only that, but there are also two other nice properties. One is that the eigenvalues from lambda 1 through lambda n will all be real. And two, V is an orthonormal basis for Cn. So in other words, V is unitary. So if we have V Hermitian V is equal to VV Hermitian is equal to the identity matrix. Okay, so V is unitary. So this is really the best case we can get. It's going to come up a little bit in a couple minutes now when we talk about the singular value decomposition. But if we can find an A that is symmetric or Hermitian in the complex valued case, that matrix will always be diagonalizable, and it also has some really nice properties. In general, for dynamical systems, This won't really occur unless we're looking at special types of problems. Can anyone think of a dynamical system that is symmetric or Hermitian? I can think of a couple examples. We actually looked at one kind of when we first looked at state space systems. So in general, diffusion or heat problems will have a symmetric system matrix. So that's one example where we are able to always diagonalize them using the spectral theorem. All right, so let me just quickly talk a little bit about, I'm not going to go into the Jordan form. I just want to show you that there are matrices that are not diagonalizable, and there will be dynamical systems that are not always diagonalizable. And in that case, instead of using the eigendecomposition, you have to use what is called the Jordan form of a matrix. So I'm not going to go through the full example because we won't be using it in this class, but it's an important thing to know. So let's take a look at just two different examples here. Let's look at a matrix defined as follows. So let's say you have 2, 0, 0, 2. So it's already a diagonal matrix. If you compute the determinant of lambda I minus A, you'll find that the eigenvalues are equal to 2 and 2. So it turns out this matrix is already diagonalized, right? So if you set it to 0, you know that the eigenvalues lambda 1, lambda 2 are both equal to 2. And if you now look for the eigenvectors, so if you take lambda I minus A times V is equal to 0, what you'll end up with is if you take 2 times I minus this matrix, you'll end up with 0, 0, 0, 0 times our eigenvector V1, V2 is equal to 0, 0. Okay. So what is the nullity of this matrix? 2, right? So our basis of eigenvectors, there will be 2 linearly independent eigenvectors that we can create to fill out our basis of eigenvectors, right? There are 2 linearly independent eigenvectors associated with the eigenvalue 2. That's what this is telling us. Let's take a look at that strange matrix that I showed you last time. Let's say it's 2, 1, 0, 2. You can find that for this matrix, if you compute the eigenvalues, your eigenvalues will also be equal to 2 and 2. So there'll be an eigenvalue 2 with multiplicity 2. But what happens when you go and try to compute lambda I minus A? You'll find that your matrix ends up being 0, -1, 0, 0 times V1, V2 is equal to 0, 0. And the nullity of this matrix here is what? 1. So this tells you that there's only one eigenvector associated with eigenvalue equal to 2. So in other words, you can't create a full basis of linearly independent eigenvectors for this matrix. The best you can do is to put the matrix into what's called Jordan form. And this matrix here is actually already in Jordan form. So basically, when you are working with a matrix in Jordan form, it will be, so you'll be able to decompose a matrix A into VJ, V inverse, where J will be a matrix of Jordan blocks. So it's kind of like an eigendecomposition, but each of these blocks will look something like this. So you'll have the eigenvalue associated with that block, and then ones above the diagonal. Okay, and if you put the system in this form, it turns out that we'll still be able to use it for our purposes later on in the class, where we will be computing the matrix exponential in particular, or computing functions of a matrix. And the Jordan form will still allow us to do that. But I wanted to just make it clear that for some matrices, you cannot compute a eigendecomposition. And actually, let me go ahead and just show you really quick. I just wanted to show you this example. Okay, it's blocking me. Okay, so here we have that same matrix we were looking at before. Actually, let me go ahead and set this to be the matrix we looked at originally. So we had 0, 1, -2, -3, right? So we can write out that matrix. We can compute the eigenvalues of A using this function in NumPy, so np.linalg.eig. And if we look at what it returns, we'll see that S is equal to the eigenvalues, and V is the matrix of eigenvectors. So if we take this product here, V times the matrix of eigenvalues times the inverse of V, this should return our original matrix. And we'll see that that's the case with a little bit of numerical error here. So this is basically 0, 1, -2, -3. Okay, so let's see what happens when we try our non-diagonalizable matrix. Oops, 2. So we have the non-diagonalizable matrix that we just tried. Let's compute the eigendecomposition, or try to compute the eigendecomposition, and let's try to reconstruct the original matrix. And it actually just returned us the eigendecomposition for the diagonal matrix of 2s, right? So it's important to know that if you just naively try to use the eigendecomposition in MATLAB or Python, it will not necessarily give you the right answer if the matrix is not diagonalizable. Okay. So it's important to know when to use the Jordan form if you need it. The process for doing that is in the course notes, but unfortunately I don't have time this semester to go through the Jordan form, but it is an important concept to know. All right. So the final concept I want to talk about today is the singular value decomposition. Has anyone here heard of the singular value decomposition? So I've actually uploaded a Jupyter notebook with some examples of applications of the singular value decomposition. First of all, who's heard of the singular value decomposition, or SVD, before? Anybody? Can you just raise your hand so I can just see? Okay, so the SVD, this is one of the most useful tools in your linear algebra tool belt. It is a generalized eigendecomposition that will work for matrices that are both non-diagonalizable and also non-square. So essentially, for any matrix, for A in R, let's just say it's in the real numbers, it doesn't need to be, in R m by n with rank R. So we can take any matrix of this form, whether it's square or non-square, and we can write it in a form that's analogous to the eigendecomposition as A is equal to U times sigma times V transpose, where sigma is a matrix of the form S 0, 0, 0, and where S are the S is the diagonal matrix of singular values from sigma 1 through sigma r. So I don't have full time to go through kind of the theory of the singular value decomposition, but essentially these singular values, sigma 1 through sigma r, these are the eigenvalues actually, let me write it like this. For sigma I of A, this is equal to the square root of the ith eigenvalue of A transpose A, which is equal to the square root of the ith eigenvalue of A transpose. Okay, so these singular values are the eigenvalues of this, what was called a gram product of A with itself. And by the spectral theorem, we know that this gram product is always going to be diagonalizable because it's symmetric. So let me just, I don't have time to go through the theory of the singular value decomposition, unfortunately, or go through the exercise that I had hoped to get through. But SVD has a lot of really fascinating applications, in particular for kind of analyzing the low rank structure of matrices or data sets. So I'm going to go through just a couple of examples of applications of the SVD. This is located up in the Canvas site under svd.ipython notebook. So you can go and run these examples if you'd like. One really interesting application of the SVD is in kind of analyzing and extracting the low rank structure of data sets or systems. So for instance, let's say we have an image. And let's say we want to take this image and we want to compress it. So the SVD is actually used for this purpose in algorithms like JPEG image compression. Essentially what you can do is once you have the singular value decomposition of a data set, you can take just the most significant singular values and throw out the less significant ones. So what I'm doing here is I'm taking this image as a matrix A. I'm computing the singular value decomposition, and then I'm recomputing a truncated version of our original matrix A, our image, by taking just the first R important singular values. So let's see what happens when I do that. Oh, I already have the example here. So this here is our original image. It's a picture of this mandrill. And this is the compressed image. So this is using only 10% of the original singular values. You get a compressed image that it uses up a lot less data because you're using a lot fewer entries in your representation of that image. Another kind of intuitive way it can be used is you can use it for extracting the most important features of a data set. So has anyone ever done principal component analysis? So often this is used when you want to, if you have a data set with many different explanatory variables and you just want to pick out the most important ones, this is one of the go-to techniques for doing that. And it really is just using the singular value decomposition and taking the most important rows of your U matrix of left singular vectors. That's all the principal component analysis is. So what I'm going to do here is I have this data set of faces. So this is a data set of, I think, 500 different images of faces. And I'm going to go ahead and take that image and I'm going to compute the singular value decomposition. So it's going to take that original data set of all of those faces together. Each row, I'm going to stack it into a matrix where each row is an image, kind of just flattened into a single array of pixels. And I'm going to take that big matrix of all those faces together and I'm going to compute the singular value decomposition. And it finished running. So what I'm going to do now is after computing the SVD, I'm going to just plot the first 10 most important singular vectors, the first 10 most important directions that were identified through the SVD. And what you get is something that looks like this. So these are called eigenfaces. Essentially, any of the original faces in our data set is some linear combination of these. And these are the 10 most important directions that essentially form the human face based on this image data set. So you have that the first image, this is associated with the largest singular value, and it's essentially just the average face from the data set. The rest of these faces kind of incorporate the most important geometry based on the lighting conditions. So you can see this face here is kind of partitioned from lighting from left to right. You have lighting from above, lighting from below, and so on. So each of these faces kind of represents the most important directions or components in your original data set. And this can be used not just for images, but also for large multi-dimensional data sets as well. And at the end of the day, it's really just the eigendecomposition or the SVD. Okay. There's a couple other examples here. So orthogonal procrustes is just an algorithm. If you want to take one matrix and map it to another one, find the transformation that maps one matrix to another. You can also do that through the SVD. So we have these two different pieces, two different geometries. We can find a transformation that maps them onto each other, even if they are rotated and stretched in different ways. So SVD is a really important tool to have in your tool belt. We won't be using it for any controls purposes because the techniques that use SVD are a little bit too advanced to get into for this class, but it is a really important tool to think about when you're thinking about dimensionality reduction or model reduction as one of the go-to methods. All right, so that's all I have for you today. On Thursday, we will get into how we can actually solve LTI systems in state space form using the matrix exponential and matrix functions. Okay, so with that, I will call it a day, and I'll see you on Thursday.